All right, we're recording now. So whatever you say may be recorded. Tangent graphs, exercise 6J is on tangent graphs, and I'm going to talk about the transformations. I'm going to talk about the period, amplitude, and the reason and thinking behind them. Okay, so let's have a look at the graph. Tangent graphs. Tangent graph, if you didn't understand, it's the relationship between the gradient of the radius, okay, gradient of the radius and the angle as you move around the unit circle. Now this is different to your sine. Your sine is a relationship between your vertical values, which is your y values. The relationship is, so you're saying, how much am I increasing vertically as I'm going around the circle and making an angle? That's your sine. So that's why we call this sine theta, opposite of hypotenuse. The other one is cos, which we then say cos theta is all your x values in relation to the theta. So these are all your y values. These are all your x values. So what is tan? Tan is the gradient, because we said tan is rise over run, which is sine theta over cos theta, which is y on x. Because it's y on x and it's sine theta over cos theta, we know that tan theta must be the gradient. So if you look at the gradient, if I'm moving, and we're going to use a different color so you can see, this is how you're getting a tangent graph. Because if you start off at 0, this is a gradient of 0, which explains why in your graph at 0, the gradient is 0, tan is 0. As you move around the circle from each point, see each point you're going around the circle, the gradient starts to increase. It starts slow, and then it starts to increase to almost a vertical line, which explains why the graph slowly increases, and it increases to a point where eventually, at pi on 2, you have a vertical gradient. And we know in year 9, a vertical gradient is an undefined gradient, which is why at pi on 2, which is 90 degrees, at pi on 2, a vertical line is undefined. That's why it's undefined at this point, and that's why it goes into infinity, and it's always positive, but it's never up until you never touch that line at pi on 2. But as soon as you pass pi on 2, the gradient is immediately negative, but is negative in a very large, because it's a very steep negative. That's why you start at the very bottom. And as you keep going around the circle, the gradient eventually reaches 0 again, which is at pi. So gradient is 0 at pi. That's why at pi, you have your x-intercept at pi. And it's 0, and then the same logic continues again. It's a slow gradient before you get very large, up until 3 pi on 2, which is why your asymptote is again at 3 pi on 2. Okay? And so therefore, if you look at the period, the reason why we say the period of pi is 1 pi, logically, it only takes 1 pi to start from 0 to get back to 0 again. Okay, and so therefore, or back from positive, back to positive again, or logically you can look at this and say that's a period of 1 pi. So therefore, tan of nx, n being your dilation factor from your y-axis, you can look at the graph and already say there's no amplitude. Unlike sine and cos graph, there was no maximum or minimum. There's no amplitude. The period now is pi times 1 on n, which is why it's pi on n. That's the reason why you got your period as pi on n. And then you got your vertical asymptotes. Now it's given by this formula. But really, if you really think about it logically, you had pi on 2, which is this vertical point, and then you got 3 pi on 2. Technically, it's every time it's vertical. So it's pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2. It's just every odd pi on 2, which is why this represents odd. 2 times a number makes it even, plus 1 makes it an odd number. So odd number times pi on 2. Now the question is, why do you have the n? Because there's a dilation factor. N will occur because you can shrink the graph thinner. So that's why you have to times it by 1 on n. The dilation factor. That's why that's your formula for all your vertical asymptotes. If your n is 1, so tan of x, then it just becomes, if k is, let's say, 0, if k is 0, then it just means that you've just got pi 0 plus 1, which is 1, 1 times pi, that gives you pi on 2, which is why that's your first asymptote. This is when k is 0. When k is 1, then you have 2 plus 1, so you have 2 plus 1 times pi over 2, and let's say n was 1, then this now becomes 3 pi on 2. So you can use this formula to find all the asymptotes. You can say when k is 1, k is 2, k is 3, k is 4, and it gives you every asymptote onwards. Or if you want to find all the asymptotes in the negative direction, well, it's k when k is negative 1, k is negative 2. So that means when you write this formula, you have to realize that k is an element of all z values, which is, sorry, not z values, integers. Integers, positive and negative whole numbers. Yeah? So I write there. No, k is element of z, that is integers or whole numbers, positive and negative. Yeah? Now, what I'm just writing here is just in case you missed out on what I was just saying just now. It's the same thing. I'm just saying from a unit circle, you can tell that the gradient's undefined at pi on 2 and 3 pi on 2, and it is every odd pi on 2. That's where the formula is coming from. So even if you've forgotten the formula, you can still derive it yourself because it's every odd. And odd is that. That's the only way to get an odd number. Times, make an even, and then add 1 to it, it makes an odd. Yeah? So that's your definition for your tan graph. That's where the tan graphs are coming from. So now we can picture what the tan graph looks like. We know these are the certain properties. This is what it looks like if we were to sketch it. Okay, so tan of n theta, n being your dilation factor, theta is the angle. So I've got axis in terms of theta. My asymptotes are all shown. It's at pi on 2, 3 pi on 2, 5 pi on 2. So it's every odd. This is your normal n equals 1 graph. This is when n equals 1. So this is a graph of tan theta, tan theta, which is 1. And so therefore, if we're talking about the domain, clearly the domain is all real values except for every time you get an asymptote, which I try to write it like that. It doesn't say in your textbook, but I just wrote it my way. And I just said it's all real numbers except for, so the backslash except for, and I just wrote the asymptote. That's 2k plus 1 times pi over 2n, providing where n is all real numbers. So n can be any number you want. It's a dilation factor. And z, so n's dilation factor. So it can be any number. And k is just your integers. And that will tell you domain. Whereas range, we can clearly look at the graph and say, oh, it goes on to infinity. So it has range of all real values. Therefore, the next part is you can then tell domain range. Y-intercept's easy. You can always let x equal 0. The hard one was x-intercepts. But the nice thing about tan graphs, even though they look weird, is actually the easiest one to draw. And the reason why is because your x-intercepts, if you notice, it's always 1. There's always one x-intercept. There's only 1. Because every time you draw one graph, it crosses once. That's it. It only ever crosses. It doesn't come back and touch it again. So for one period, you get one x-intercept. And the nice thing is it's always a distance of pi. And the reason why is you think about the unit circle, the x-intercepts occur when tan of theta equals 0. This is when your y values are equal to 0. So if y equals 0, the question is when is your gradient? Tan theta means gradient. When is gradient equal to 0? That's all you're asking. You're just asking when is gradient equal 0? And if I had to answer that, well, I'm just looking at the graph and I'm saying, well, it equals 0 every time you pass those points. And these points are 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. That's what they're doing here. You can see it's crossing 3 pi, 2 pi, 1 pi, 0. So even if you had a dilation factor only affects whether you shrink it or you expand it. And so you're just taking pi divided by 2 if it's 2 pi. Okay, so if it's tan, if it is tan of 2x, that's a dilation factor of half from the y-axis. So if your normal intercepts are at pi, then now it becomes pi times half, pi and 2. That's why I've got this formula as n, that's a dilation factor. This is your dilation factor. And k is just your integers. So if you want to know the first intercept, well, when k equals to 0, then what you're going to have is you have x-intercepts is equal to 0 times pi on n, in our case is 1, then 0 times pi is 0. That's why you have intercept at 0. If you want to find the next one, this is when k equals 1. So if k equals 1, same thing, you've got 1 times pi on 2, on 1, because n is 1, then it gives you pi. It's true. So you can use this formula to find out all x-intercepts if you didn't understand the unit circle, and you can use this formula to find all asymptotes. And you just sketch. So tan graphs compared to sine and cosine, this is actually the easiest one to do. It's really easy to find out your x-intercepts and your y-intercepts, okay, even though they look really hard. But what I want you to take out of it is a tan graph is just a gradient as you're going around the circle. And if you can picture that, it is so easy to tell when is tan or when is the gradient negative or positive. Very simple. Just keep in mind y values are your sine, x values are your cos, gradient is your tan. That's what it is. Okay? All right. Now, these ones I've been repeating the same things over and over. Your transformations that you learnt in chapter 3 apply to sine graph, cosine graph, and it applies exactly the same for tan graphs. You know that A tells you dilation factor of A from the x-axis. You know that n, which is dilation factor of 1 on n, that's the key thing. That's why your period formula is pi on n, okay, which I've shown here. Period equals to pi times 1 on n, which gives you pi on n. And then you've got your, to find out if you're moving the graph left or right, I told you to let nx plus b equal to 0. It's been the same throughout quadratics, cubics, and every other graph. So if you solve for x, if it's positive, it moves to the right. So if it's positive, it moves to the right. If it's negative, it moves to the left. That's the same technique you've been using over and over. Yeah, so if I gave you, for example, tan of x minus pi on 3, if you solve for this, if you had said, all right, let's let this equal to 0, x minus pi on 3 equal to 0, then you therefore x equals to pi on 3. This just implies that you're moving to the right by pi on 3 because it's positive. It's positive pi on 3. And then finally C, translation up or down by C units. Positive is up, negative is down. Yeah? And so you're applying the same thing. This is now how to sketch using transformations. I gave you the properties. I gave you the meaning of what a tangent graph is. So we look at this example. Sketch the graph of y equals 3 times tan of 2x minus pi on 3. Yeah? First things first, let's read the transformation. We've got 3 dilation factor from the x-axis. So it just means it gets stretched, it's thinner, it's longer, vertically. It's got a 2. That tells me it's dilation factor of half from the y-axis. So that means it gets shrunk by half. So it's thinner as well. So not only is it thinner vertically, it's also thinner in your x-axis. That means you get more cycles from the same period. If you solve for 2x minus pi on 3 equals 0, you'll find that that means it's moving to the right by pi on 6. And then I just wrote here just so that you remember, if you let 2x minus pi on 3 equals 0, solve for x, that gives you pi on 6 to the right. Yeah, so I read the transformations. I know it's thinner and it moves to the right. So that also tells me, as immediately, I already know the first x-intercept, it was at 0, and I move it to the right by pi on 6. My first intercept is at pi on 6. If I wanted to find the next one, it's the period. And the period right now, which I can tell, it's pi on n, and n is 2, so my period's pi on 2. So if I really wanted to know all my x-intercepts right now, it starts off at, it would have started off at 0, and it moved to the right by pi on 6, so it's now at pi on 6. If I want to find the next one, add pi on 2. Want to find the next one, add pi on 2. And you're going to get all your x-intercepts, because I haven't moved this graph up or down. So it doesn't change that, it's just moving left or right. I can say just add pi on 2, add pi on 2. But let's say you didn't like that. Let's say you wanted to use the formula. We can use the formula to find out the x-intercepts, the amplitudes first, and then find the x-intercepts. Notice I wrote here, I said the amplitude, this formula here would give the amplitude, but you gotta remember, because you're shifting your graph by pi and 6 to the right, that means your asymptotes also shift to the right by pi and 6, which is why I have plus pi and 6. So if you want to find all your asymptotes right now, it would have just been when k equals to 0, if k equals 0, you get pi and 4, because n is currently 2. So if you want to find your first asymptote when k equals 0, you get pi and 4, plus whatever pi and 6 is. You want to find out the next one is when you have k equals 1. So if k equals 1, you'll have 3 pi and 4 plus the pi and 6. So if you want to find all your asymptotes, that's your formula right there. Yes, Katie?
On the slide, you say dilation factor apart from the y-axis. I'm pretty sure it should be the y-axis, but on the slide before you said it's the dilation from the exact.
Oh, did I? On the slide before. I don't know how to go back. Let's do it this way. Oh, thank you. I'll fix that. And for the video, it is from the y-axis. And that is correct. Cool. Okay. And then finally, the x-intercepts. If you didn't like the approach I showed you just now, that you knew the period and you knew they're translated by right, then you can use the formula. The formula I said before was k times pi on n, which I know k, let's say it was 0. If it was 0 and n was 2, then it's pi on 6. But don't forget, you have the translation. So don't forget, the translations do affect it. Whether you go up or down, it will affect your overall result. Okay, so think about your transformations. When you write out your transformations, I want you to pay attention to the transformation because it affects your x-intercept or y-intercepts. Okay? Yes? Is it supposed to be asymptotes, not amplitude? Oh. I'm on a roll. Thank you. Asymptotes, yes, not amplitude. Don't know what I was thinking. Don't forget translations. Okay, so once you do that, this is the graph of what it should look like. This is the example from your textbook. Well, what I want you to see is everything that I wrote here, I'm just using logic and understanding of the tan graph, and I could find all my asymptotes, which is all given 5, 11, 17, 23, based off this concept. And the same thing with the x-intercepts. By logic, I knew the first one was pi on 6. And adding to the next one to get to 2 pi on 3, add pi on 2. So that's what I was saying. I was saying to move from this point, you're just moving by a period of pi on 2. Okay, so for each one of these, that's your tangram, and that's what that exercise 6J is about, is testing. Do you understand the properties of a tan graph? Did you understand the transformations? Do you understand the symmetry properties? And that goes back to what I was saying at the very start. The study point that you need to understand is, can you read the transformations? Do you understand the properties? And the only way to understand the properties is if you understand what tan of theta is. And it's just the gradient. So that's all I've been trying to say. It is the gradient of your unit circle. It's a gradient of your radius as you move around the unit circle. Okay? So that concludes for exercise 6J. Now, these are some past exam questions. They're pretty straightforward. This one is actually on Schoology already, so if you want to do it, you can do it there. Or you can have a look at this, and I've got another one, so there's two. From VCAA 2003, question 7 and 8. Question 8 might be a bit trickier. So I'm going to give you probably about 2 minutes to do this one. This one you should be able to pick up straight away. And this one I'll give you 3. Okay, but it shouldn't take that long. It should be about 2 minutes each. Oh, sorry, about 2 minutes in total. Okay, so let's go. Let's time that now. That's now. I can't read my time. That's 11:21. So I'm going to give you to 20. Sorry, not 21. 26. So I'll give you to 28, and then I'll move on to the next one. Okay. Have a look at this one. Period of the circular function is. C. How do we know it's C? How did you do that? Yeah. Well, you just think from here to here. It's at 7 pi on 4 to 3 pi on 4. Well, distance is 4 pi on 4. Just a pi. Well, C. Straightforward. Yeah? Let's go with this one then. I want you to tell me which one is the correct answer. I know which one it is, but you have to use all the properties I just taught you. So you're looking at this graph, it's now a sine graph, but you're reading transformations, you're reading the period, so symmetry properties, and then understanding which graph should this be. Now you should be able to eliminate some of these solutions already. You should already know which ones aren't the possible solution, and you got to keep on to what you think may be the solution. And remember, it's VCAA, so they'll try to trick you. So you need one extra step that takes a bit of work. No, not doing this. Present. All right. Let's go through the answer. Can I get a show of hands who got A? Can I get a show of hands who got D? And let's show of hands who got E. Okay, first off, we know that it can't be E because this is a sine graph, it hasn't moved left or right. So that means the origin, sine of 0, whatever this is, when x is 0, sine of 0 has to give you 0. So that means if you have now 0, 1, logically it means the graph has shifted up by 1. This is the only one that's responsible for going up 1. So that means Q has to be positive 1. So it can't be E, negative 1. So that means up 1. You can look at the period, you know it's a distance of 4. Now I told you the period of a sine graph is normal 2 pi divide n. Our n value is currently k pi, which is why I've solved it over here. 2 pi divided by n, pi's cancel out, and if you switch the k and the 4, k equals half. That's why I knew these two are wrong. So now you're left with A and D, and this is why I said it's up to you now. It's VCAA, they're going to test whether you know it's positive or negative. Now the only way to do this is you gotta use your understanding of, well, it's an amplitude. Yeah, you know the amplitude is currently +2. Yeah, but if you think about logically, at 1, this tells me that the coordinate is -1. Now, so far, this is what I have. I've got f of x equals to p times sine of half, or pi. What happened there? Wait, uh-oh. Woo! I thought I lost that there. If it's, no! Pi on 2 x plus 1. So this is my equation so far. I got pi on 2x plus 1, and I know this coordinate, 1, -1. So that means if this is -1, my y values, and x is 1, now sine of pi on 2, we know is 1. So if I rewrite this equation up here, I'd have -1 equals to p multiplied to sine of pi on 2, which is 1, because when x is 1, 1 times pi on 2 is pi on 2. So sine of pi on 2 is 1, and then plus 1. So this really gives me -1 equals to p plus 1. Therefore, p minus 1 on both sides is -2. So it's actually a negative sign graph. And you can actually look at it and say, well, the graph hasn't moved left or right. So the only way for it to actually look like this bottom half is if it was a negative graph. And so therefore, the answer had to be D. Now I can see why people would have chose A, but it's not. Okay? And that's how you prove it. There you go. And that is recorded, and I'm going to now save this.